So we're studying inner product spaces. And for a vector space V, the inner product of two vectors, x and y, is a positive definite symmetric bilinear form on the set of ordered pairs of vectors in V. So positive definite means if you take the inner product of a vector with itself, that's always positive for all x different from 0. Symmetric means the inner product of x and y is the same as the inner product of y and x for all x and y in the vector space. And bilinear means if you have, say, c1x1 plus c2x2 inner product with y, that's c1, the inner product of x1 with y, plus c2, the inner product of x2 with y. So these are the properties of a inner product, of an inner product. We say that vectors x and y are orthogonal or perpendicular, mean the same thing, if the inner product of x and y is 0. And without even reference to the inner product, vectors x and y are parallel if x and y are different from 0, and one is a scalar multiple of the other. Y is c times x for some scalar c. And one of the nice, we also define the length of a vector length of a vector x is written as x with these absolute value signs around it. Sometimes you use double, sometimes you use single. If we take the inner product of x with itself, that's positive. If x is non-zero, if it's positive, you can take the square root, and that's defined to be the length of the vector x. And a unit vector is a vector u of length 1. That is, the length of u is 1. That's a unit vector, just means unit length. And we have the length of c times x for any scalar c is the square root of cx, that inner product. But you can take the c out and the second c out, that's c squared xx. Square root of c squared is the absolute value of c times the square root of xx. So the length of c times x is just the absolute value of c times the length of x. And so in particular, if x is different from 0 and c is 1 over the length of x, then and if we define u to be the vector 1 over the length of x times x, so we're multiplying x by the scalar 1 over the length of x, then the length of u is the length of 1 over the length of x times x. We can take this scalar outside. You get 1 over the length of x times the length of x. These cancel. This is 1. So this is always a unit vector. If you take a vector and divide by its length, you get a unit vector. If you have two vectors, let's say x and y, it's possible to decompose x into a component of the vector parallel to y and a component perpendicular to y. If I want to use the same notation that I used yesterday, I took vectors v and w. So this is the vector v, this is the vector w, and I want to be able to write v as the sum of a vector parallel to w and a vector orthogonal or perpendicular to w. And the inner product allows me to do that. Suppose I let v1 be a unit vector in the direction of w is 1 over the length of w times w. This is a unit vector in the direction of w. So if I take the inner product of v and u times u, well, this is a scalar times u. What is this? This is the inner product of v and w over the length of w times u, which is w over the length of w. I can take these two scalars out. This is the inner product of v and w divided by the length of w squared times w. So this vector is parallel to w. And suppose I let v2 be v minus v1. So that's v minus the inner product of v and w divided by the length of w squared times w. I claim this v2 is perpendicular to w. So how do I do that? I have to compute the inner product. The inner product of v2 and w, that's v minus vw over the length of w squared times w, inner product with w. By bilinearity, that's the inner product of v and w minus the inner product of this with w. I can take this scalar outside, vw over the length of w squared times the inner product of w with itself. But the inner product of w with itself is the length of w squared. The definition of the length of w is the square root of this, so this is the length of w squared. These cancel, so I get vw minus vw is 0. So this is the projection of one vector in the direction of another and the orthogonal component of the vector with respect to the other. So for example, let's draw a simple example if I can. So suppose I take w to be the vector 4, 1, and and v to be the vector 2, 3. So I want to decompose v into a vector v1 parallel to w and v2 perpendicular to W. So W is 4, 1, V is 2, 3. So my vector V1, this was our formula, the inner product of V and W divided by the length of W squared times W. So the inner product of V and W, this is the standard inner product, the sum of the coordinates, products of coordinates. This is 2 times 4 plus 1 times 3 divided by the length of W squared, which is 4 squared plus 1 squared, times W. This is 8 plus 3, 11 over 17 times W, or that is 44 over 17, 11 over 17. That's the vector W V1. And V2 is V minus V1. That's 2, 3 minus 44 over 17, 11 over 17. So 2 is 34 over 17. So this is minus 10 over 17. And 3 times 17 is 51 minus 11, 40 over 17. That's the vector V2. And we can check. So let's see. So if I take V1 plus V2, V1, this is V1, is 44 over 17, 11 over 17, plus V2 minus 10 over 17, 40 over 17. That's 34 over 17, 51 over 17, which is 2, 3, which is V. So that checks. And let's check that V2 is perpendicular to W. The inner product of V2 and W, this is V2 minus 10 over 17, 40 over 17. Inner product with W, which is 4, 1. So that inner product is minus this, minus 40 over 17, plus 40 over 17, which is 0. So that also checks. V2 is perpendicular to W. So this is a simple example of taking a vector V, a vector W, and decomposing V into a component parallel to W and a component perpendicular to W or orthogonal to W. So recall vectors V and W are orthogonal if the inner product is 0. And orthogonal basis for a vector space V of dimension n is the basis B consisting of vectors V1, V2 up to Vn, which are mutually orthogonal, such that Vi, Vj is 0 for all I different from j. An orthonormal basis for V is the basis B with n vectors that is orthogonal Vi, Vj equals 0 for I different from j, And every basis vector vi is a unit vector. That means that the length of vi is 1 for all I, or equivalently, the square root of vi is 1 for all I, or if you square that, the inner product of every vector with itself is 1. So another way of writing that is B is an orthonormal basis if the inner product of Vi and Vj is 1 if I equals j, 0 is I is different from j, and this is exactly the function we call delta sub ij, the Kronecker delta. The Kronecker delta, delta ij, is a number that's either 0 or 1. It's 1 if I equals j, 0 if I is different from j. So an orthonormal basis is defined by the fact that the inner product of every two basis vectors is the Kronecker delta. And for example, the standard basis E1 up to En, for our n is the basis where E sub j is the vector where every coordinate is 0 except the jth coordinate, which is 1. So for example, well, this E sub n. So E2 is the basis with the vectors 1, 0, and 0, 1. E3 is the standard basis. Its vectors are 1, 0, 0, 0, 1, 0, and 0, 0, 1, and so forth. In general, E sub j is the vector whose coordinates are delta 1j, delta 2j, down to delta nj. Well, this is the Kronecker delta. So these coordinates are all 0 except the jth coordinate, which is 1. And in fact, if you want to do a little algebraic exercise, if you take the inner product of say EK and EL, so EK has coordinates delta IK and EL has coordinates delta IL. This is summation delta IK, delta IL. I goes from 1 up to n. EK is the vector delta 1k, delta 2k, down to delta nk. EL is the vector delta 1l, delta 2l, down to delta nl. When you take the dot product, the inner product, you get EK-EL is delta 1k, delta 1l, plus delta 2k, delta 2l, and so forth, down to delta nk, delta nl. So in sigma notation, this is what it is. Now, this is 0 if k is different from I, or if L is different from I. Sorry, so whenever I is different from k or L, this is 0. The only time this is not 0 is when it's 1. The only time it's 1 is when I equals k and I equals L, which means k has to equal L. And when k equals L, so this is 0 is k is different from L. And if k is equal to L, this is 1. This is exactly 1i equal to k. That's just another demonstration that the standard basis vectors are orthonormal. And we can say the following. In general, let E1 up to En be an orthonormal. Let me do this on another piece of paper. Let me see. Let E1 up to En be an orthonormal basis for a vector space V. Let V be any vector in V. Then V has some unique representation, C sub I, E sub I. I goes from 1 up to N. If this is a basis for V, every vector is a linear combination of the basis vectors. How do we compute C sub I? If I take the inner product of V with the basis vector EJ, that summation C sub I EI, I goes from 1 up to N, inner product with EJ. By the bilinearity of the inner product, this is summation. I goes from 1 up to N, C sub I, EI, EJ, inner product. But if this is an orthonormal basis, the inner product of EI and EJ is delta IJ, the Kronecker delta. This is 0 except when I equals 1. When I equals 1, this is 1. Sorry, when I equals J. So this is equal to C sub J. So in this representation of V as a linear combination of the basis vectors, in fact, the coordinate for every J, the coordinate C sub J or C sub I, is the inner product of V with EI. And this is sometimes called the Fourier coefficient of the vector V with respect to the orthonormal basis. So if you have an orthonormal basis for a vector space, for any vector V, the ith Fourier coefficient is just the inner product of V with the ith basis vector. And that number is the coordinate of V. So the coordinate vector for V with respect to the basis E is this. It's just the definition of the coordinate vector of a vector with respect to a basis. Now, orthonormal bases are nice for many reasons. And there is a method called the Gram-Schmidt orthonormalization method, or if you like, algorithm, which converts a basis for a vector space V, say V1 up to Vn, to an orthonormal basis, let's say E equal E1 up to En, with the following property. For every K from 1 up to N, the subspace of V spanned by the first K vectors of the basis B is exactly the subspace of V spanned by the first K vectors of this orthonormal basis we've just constructed. And The method to construct an orthonormal basis from a basis is geometrically very simple. I'll describe it basically. So the method. Step 1, construct an orthogonal basis. That's the hard part, a basis where the vectors are mutually perpendicular. Step 2, divide each of these basis vectors by its length to get so every vector in the basis now has unit length. So to get an orthonormal basis. So suppose you have a basis B, V1, V2, V3, Vk up to V sub n. How do we construct the orthogonal basis? So this is a basis. So these vectors are linearly independent and they span the whole vector space, which has dimension n. So suppose we let W1 be V1. That's easy. Now, let W2 be equal to V2, but from V2, I just subtract the component of V2 parallel to W1. So subtract, what is the component of V2 parallel to W1? It's V2 W1 divided by the length of W1 squared times W1. So just this is the component of V2 parallel to W1. So we can draw a picture like this. Let's say parallel to V1. So we have V1, sorry, component of V2 parallel to W1, just what I said the first time. So we got W1, then we have this other vector V2. And V2 has a component parallel to W1 and a component perpendicular to W1. If we subtract off from V2 the component parallel to W1, W2 is the piece that's left, which is perpendicular to W1, which is what we wanted. So now we have W2, that W3, oh, and also you'll see the space spanned by W1 is the same space spanned by V1 because they're the same vector. Here I have W1 and W2. W2 is in the space spanned by V1 and V2, but V2 it's a linear combination of W1 and W2. So V2 is in the space spanned by W1 and W2. So V1 and V2 spans the same subspace of the vector space as V1 and V2. For W3, we take V3 and we subtract the component of V3 parallel to W1 and W2. So V3 W1 inner product over W1 length squared W1 minus V3 W2 inner product over the length of W2 squared W2. And we continue in this way. when we've constructed the first k minus 1, or let's say the first k vectors of this new basis, we let wk plus 1 be vk plus 1 minus the sum for all I going from 1 up to k, the component of vk plus 1 in the direction of wi. That's this somewhat scary looking function, but this gives us a new vector. And this new vector is perpendicular to all the w's we've constructed previously. And we just continue this process. This is the algorithm. And there's some examples in the notes, and I worked out in the printed notes, and there's an example I did in class yesterday. I mean, it takes a lot of time, it's work, to use this Gram-Schmidt process to construct an orthonormal basis, but it will work. This process gives us an orthogonal basis, and then at every step we divide by the length, and we get our new vector. We get the orthonormal basis of unit vectors. Okay. Now, there are a few more things, not too many, that I want to say about inner products. I mean, all of these things were barely scratching the surface of what's known. But I should define just one other thing, which is, well, a couple other things. Suppose we have B consisting of n vectors, let this be an orthonormal basis. Well, let's make it, suppose it's an orthonormal basis just for Rn. So let's suppose that Vj is the vector A1j, A2j, down to ANJ. And orthonormal means that the inner product of Vj with itself, which is summation a sub ij squared, I goes from 1 up to n. This is the length of Vj squared, which is 1. And the inner product of Vi and Vj for I different from j, the summation I goes from 1 up to n, a sub this a sub v sub j, v sub k, for j different from k. So Vj has coordinates aij, Vk has coordinates aik, and this sum is 0 if j is different from k, because these vectors are orthogonal. Suppose I write the matrix A, whose columns are these coordinate vectors. So A11, A21, down to AN1. Second column is the second vector, A12, A22, down to AN2. The last column will be A1n, A2n, down to AN. Now, A transpose is the vector you get by interchanging the rows and columns. So the first column becomes the first row. The second column becomes the second row. Down to the nth column, the nth column becomes the nth row. And if I take A transpose times A, so these are both n by n matrices, I can multiply them. So what is the ijth coordinate of this? You get the ijth coordinate of a matrix by multiplying the product of two matrices by multiplying the ith row into the jth column. So this is summation, say k goes from 1 to n. The ith row elements are a, I, k. I'll write transpose. It just means the ikth entry of AT times the kjth entry, AKJ. Well, for the transpose, the ikth entry of the transpose is the kith entry of the original matrix. So this is AKI, AKJ. K goes from 1 up to n. And this is exactly the inner product of the vector VI and VJ. VJ has coordinates A1J down to ANJ. This goes A1J down to ANJ. This is the Kronecker delta. So this matrix has its ijth coordinate, the Kronecker delta. That means this is the identity matrix. A transpose times A is the identity. And similarly, if you calculate A times A transpose, the ijth coordinate of that is summation AIK A transpose KJ. K goes from 1 up to n, which is summation K goes from 1 up to n, AIK AJK. Instead of doing this, it's easier just to do the following. So we have A transpose A is the identity. So the transpose of A transpose A is the transpose of the identity. But the identity is symmetric, has ones down the diagonal and zeros everywhere else. When you take the transpose, it doesn't change. But the transpose of a product of two matrices is the product of their transposes in the opposite order. So the transpose of A transpose A is A transpose, A transpose transpose. When you transpose the matrix twice, you're back where you started. This is A transpose A. No, that didn't help. Let's just leave it this. A transpose A is the identity, which is the lemma in the notes. So there we are. Let's see. There's much more I could say, but time is short. And I want to prove what is one of the most important identities in algebra, linear algebra. And mathematics in general, which is Bessel's inequality and the Cauchy-Schwarz inequality. So let's say V is an inner product space, and we have an orthonormal basis E consisting of n vectors E1 up to En. So these are mutually perpendicular or mutually orthogonal vectors, all of length 1. Then, if we let C sub I be the inner product of the vector V with EI, so let V be a vector in V, in the vector space V. Let C be, this is the Fourier coefficient, the inner product of the vector with the basis vector. And the Bessel's inequality says if you take the sum of the squares of these coordinates, these Fourier coefficients, this is less than the length of the vector V squared. So we have the coordinate vector for V with respect to the basis E is C1, C2 up to C sub n, and the sum of the squares of those coordinate vectors is less than or equal to actually, what I'm going to prove is a little bit stronger. So let me restate this. This is true, but I want to state this better. So Bessel's inequality, we have a set E1 up to En, orthonormal vectors in V, not necessarily a basis, it could be just a subset of a basis, for example. That V be a vector in the vector space, and let C sub I be the inner product of V with E sub I, it's what we call the Fourier coefficient. And then summation C sub I squared, I goes from 1 up to n, is less than or equal to the square of the length of the vector V. So this is just a long calculation which maybe I'll start on so I have a whole piece of paper to write on. So we have E1 up to En, orthonormal, the vector V in the vector space V, and C sub I is the inner product of V with E sub I. Let V prime be V minus summation Ci Ei, I goes from 1 up to n. So we have an inner product space V, vector space V. We have n orthonormal bases. You take any vector in the vector space and let Ci be the inner product of V with Ei. And I want to show that the sum of the squares of these Ci's is at most the length of the vector space, and the square of the length of the vector V. So I define V prime to be this. So the inner product of V prime with itself, the inner product of any vector with itself is positive if the vector is positive, is non-zero, and 0 if the vector is 0. In any case, this is greater than or equal to 0. So what is that? V prime is V minus summation Ci Ei, inner product with V minus summation Ci Ei. I goes from 1 up to n. So if I expand this by bilinearity, this is the inner product of V with V minus the inner product of summation Ci Ei with V. So that's V with V and V with this. And then I have this with this minus, sorry, I have this with this, this with this. And then I have this with this. So that's minus the inner product of V with summation Ci Ei. I goes from 1 up to n. And the inner product of this with this, minus times minus is plus. So plus the inner product of CI, EI, I goes from 1 up to n. All right, this is summation CJ, EJ. J goes from 1 up to n. So this is the inner product of V with V. Minus 2 times, because this, the inner product is symmetric, so the sum with V inner product is the same as the inner product of V with the sum. So this is the same as 2 times the inner product of V with the sum. Plus, now this inner product, if I just expand this by bilinearity, I get a sum. I goes from 1 up to n. J goes from 1 up to n. I have all pairs I and j, Ci, Cj, inner product of EI and EJ. Okay, good start. What is this? This is the inner product of V with V. Plus, again, I can take this sum out by bilinearity, minus 2 times summation I goes from 1 up to n, V C sub I, sorry, 2 times summation Ci, inner product of V with EI, plus, but now this EI, EJ, that inner product is delta IJ. That's 0 except when I equals J. When I equals J, I get C sub I, C sub I, C sub I squared times 1. DE sub I, that inner product, is by definition C sub I. So this is the inner product of V with V minus 2 times summation I goes from 1 up to n, C sub I squared, plus summation I goes from 1 up to n, C sub I squared. This is the inner product of V with V minus summation C sub I squared, I goes from 1 up to n. That's all greater than or equal to 0. So I bring this on the other side, I get summation C sub I squared, I goes from 1 up to n, is less than or equal to the inner product of V with itself, with this length of V squared. That's what I wanted to prove. That is Bessel's inequality. Let me just pause for 1 second. Good. So that was the proof of Bessel's inequality. And I want to also prove the Cauchy-Schwarz inequality, which is one of the fundamental facts of linear algebra. So Cauchy-Schwarz. Sometimes people think it's Schwartz with a T, but it's Schwartz without a T. Cauchy-Schwarz inequality. Again, we have an inner product space V and vectors u and v in this vector space, the Cauchy-Schwarz inequality says the inner product of u and v in absolute value is always less than or equal to the length of u times the length of v. So let me just notice the special case that you should see in calculus. Suppose we take v to be R3 and u to be x1, x2, x3, v to be y1, y2, y3. Then the inner product of u and v is x1, y1 plus x2, y2 plus x3, y3. The length of u is the square root of x1 squared plus x2 squared plus x3 squared. The length of v is the square root of y1 squared plus y2 squared plus y3 squared. So the inequality says that the absolute value of x1, y1 plus x2, y2 plus x3, y3 is less than or equal to the square root of x1 squared plus x2 squared plus x3 squared times the square root of y1 squared plus y2 squared plus y3 squared. One usually sees that by after you square both sides, which says that x1, y1 plus x2, y2 plus x3, y3 squared is less than or equal to the product of the sum of the squares of the x's times the sum of the squares of the y's. And this extends from vectors in dimension 3 coordinates to n dimensions. But this is a very beautiful inequality which is used everywhere in mathematics. It's really a fundamental fact. And the proof depends, so the proof of the general case and the particular case depends on knowing something about quadratic equations. Suppose you want to solve the quadratic at squared plus bt plus c equals 0. So you know the quadratic formula. T is minus b plus or minus the square root of b squared minus 4ac over 2a. And b squared minus 4ac, if this is 0, there's one root. If this is positive, there are two roots, because you have a positive square root. If this is negative, there's no root in the reals, because you have to get to the complex numbers. So the number of solutions of this quadratic depends on the sign of b squared minus 4ac. Positive 2 roots, 0, 1 root, negative no roots. So that's something which you have to have learned long ago. Okay, so what we want to prove in Cauchy-Schwarz is for any vectors u and v, the inner product of u and v is less than the length of u times the length of v. So the idea is to consider So we want to consider the vector tu plus v. So we have vectors u and v. T is a scalar. What's the square of this length of this vector? You take the inner product of the vector with itself. When you expand this, you get, but using the bilinearity of the inner product, I'll do this. This is tu plus v tu v v, inner product v with v. I can take the t out of this. This is the inner product of u with u times t squared. Here I have 2 inner product u v vu, but they're the same. And I can take out a t. So I have 2 times the inner product of u with v times t plus the length of v squared. And this is greater than or equal to 0 because the square of the length of a vector squared is not negative. So this is a quadratic equation, and it's always greater than or equal to 0. If you were to graph that, this function of t, it's function of t is a parabola, it's either strictly greater than 0 everywhere, or it touches the x-axis at one point, but it's never below the x-axis. So this quadratic polynomial does not have two distinct roots. That can't cross the x-axis at 2 different places, or at some point it would be below the x-axis. This is a quadratic with a positive leading coefficient, which means the discriminant is less than or equal to 0. If the discriminant were positive, you would have 2 roots. The discriminant is b squared minus 4ac. This is a, this is b, this is c. So b squared 4 times the inner product of uv squared minus 4ac. A is u squared. C is v squared is less than or equal to 0. Cancel the v's, cancel the 4's, bring this to the other side. We have uv squared is less than length of u squared, length of v squared. Take square roots. Square root of uv is less than or equal to the length of u times the length of v. So just recalling the baby facts about quadratic equations, we proved the Cauchy-Schwarz inequality. And from this, we can get a nice inequality, which is the triangle inequality. In the notes, this is theorem 9. It says that the length of u plus v is less than or equal to the length of u plus the length of v. We call this the triangle inequality because if you have a triangle, if this side is u and this side is v and this is w, in a triangle, the length of any one side is less than the sums of the lengths of the other 2 sides. And actually, I'll go up like this. So we have u we have V. This is U plus V. The length of one side of a triangle is less than the sum of the lengths of the other two sides. That's what this says. And related is a nice inequality. It says the length of U plus V squared plus the length of U minus V squared is 2 times the length of U squared plus 2 times the length of V squared. So the proof let's see. The length of U plus V squared, that's the inner product of U plus V with U plus V. That's the inner product of U plus 2 times the inner product of U and V plus the inner product of V and V. That's less than or equal to the length of U squared plus this 2 times UV. The number is always less than or equal to its absolute value plus the length of V squared. But Cauchy-Schwarz says that the inner product of U and V is less than or equal to the length of U times the length of V. So this is less than or equal to the length of U squared plus 2 times the length of U times the length of V plus the length of V squared, which is exactly the length of U plus the length of V all squared. If you take the square root, you get the length of U plus V is less than or equal to the length of U plus the length of V. Okay. That's the proof of this, and this I'm not going to prove. Okay. Let's go back to linear transformations. So V is a vector space, and a linear transformation T from the vector space to itself is called a linear operator. So you can picture it somehow like this. Here's V, and every vector V gets sent to some vector T of V in V. Now suppose sitting inside of V, there's a certain subset or subspace W, where for every vector in this subspace W, T of W, we know it's somewhere in V, but maybe it stays in W. So we say that the subspace W of V is T invariant if T of the vector W is in the vector space W for all vectors W in W. Okay. That's an invariant subspace. Let me just pause for 1 minute. So a subspace of a vector space V is invariant with respect to some linear operator T if every vector in W gets mapped into something in W into T. Now, you can see somehow if you're trying to understand a linear operator that suppose you had your vector space V and you could divide it up into two pieces, two subspaces, W1 and W2, and each were invariant. So suppose V is somehow W1 and W2, and they're disjoint. W1 intersect W2, just only share the zero vector. And every vector in W1 gets mapped to something in W1, and every vector in W2 gets mapped to something in W2. So V sort of decomposes into invariant subspaces. And if you want to understand T acting from V to V, it's really enough to understand how T acts on the smaller space W and how T acts on the smaller space W2. And somehow you might think that an operator acting on a small vector space is easier to understand than an operator acting on a big vector space. Now, the simplest subspaces, or the smallest subspaces, are one-dimensional. That is, the subspace W, which consists of all scalar multiples of a single vector E. That's a one-dimensional subspace. And this one-dimensional subspace is T invariant if T of E stays inside of W. But W is the set of all scalar multiples of E. So T of E is equal to lambda E for some scalar lambda. What this says is, in your vector space, you have the vector E and you apply T to it. It just stretches E by a factor lambda. If lambda is positive, it just looks like that. If lambda is negative, it's going still parallel to E, but going in the opposite direction. But it lies somewhere on this one-dimensional subspace. Those are like the simplest invariant subspaces, and they are the object of a lot of attention in the mathematical world, also in the physical world, because they describe lots of things about atoms and nuclei and such things. So these are the following definition. So T from V to V is a linear operator. We say that a non-zero vector E in the vector space is an eigenvalue, E-I-G-E-N, E-A-L-U-E. It's an eigenvector, excuse me. It's an eigenvector with this one-dimensional space spanned by E is invariant under T, which means E is an eigenvector with eigenvalue. So these are really words you have to know and love. With eigenvalue lambda, if T of E is lambda times E. So we say a number lambda is an eigenvalue if there's a vector E non-zero such that T of E equals lambda E. So these are simply, so the eigenvectors are vectors which are simply stretched by your linear operator. They're very simple one-dimensional subspaces. And what would be really nice is, suppose V has a basis of eigenvalues, so of eigenvectors. E1, E2 up to En, where T of EI is lambda I EI. What is the matrix for T with respect to this basis? Let me call this script E. Well, E1 goes to lambda 1 E1. E2 goes to lambda 2 E2. E3 goes to lambda 3 E3. En finally goes to this. The matrix for T is a diagonal matrix. So if you have a basis of eigenvectors for a linear transformation, the matrix is really as simple as it can be. It's a diagonal matrix. You have the eigenvalues down the main diagonal and everything else is zero. So, and in fact, if you want to understand the linear transformation or a linear operator, you try to see whether it has a basis for a basis consisting of eigenvectors, and then the matrix is diagonal, and it's very, very, very easy to work with if you need to work with it. So, how to find eigenvalues and eigenvectors if they exist. They don't always exist. For example, suppose you take the linear operator, which takes the vector v and rotates it by an angle alpha, r alpha, rotation. A rotation operator has no eigenvectors because no vector gets stretched. No matter what vector you start with, non-zero vector, it doesn't end up pointing in the same direction. It's rotated by an angle alpha. The only time it ends up pointing in the same direction are the two trivial cases. You have the identity. Every vector gets sent to itself. That's a rotation by zero. Or you have a rotation by pi, which sends everything around so your vector is pointing in the exact opposite direction. But if you take an angle alpha not equal to 0 or pi radians, rotation by alpha is a linear transformation and there are no eigenvectors. So you can't always find eigenvectors. They don't always exist. But let's see when, let's just try to find one. Or determine if there doesn't. Suppose we have, say, T from R2 to R2. And with respect to the standard basis, let's say T of xy is given by the matrix A, B, C, D of xy, which is ax plus by cx plus dy. And we want to know, so if xy is an eigenvector with eigenvalue lambda, then T of xy is just going to be lambda xy, which is lambda x, lambda y. So for this value lambda, you have x and y, where ax plus by equals lambda x, cx plus dy equals lambda y. So if lambda is an eigenvalue, you can solve these two equations in two unknowns. let's see, if I put everything over on one side of the equation, this is lambda minus a x minus by equals 0 minus cx plus lambda minus dy equals 0. So if lambda is an eigenvalue, these two equations and two unknowns have a non-zero solution. So you have xy different from 0 solves the equations. Well, the condition for two equations and two unknowns to have a non-trivial solution is that the determinant is 0. So the determinant, lambda minus a minus b minus c lambda minus d, which is lambda minus a lambda minus d minus bc, is 0. Or lambda squared minus a plus d lambda plus ad minus bc equals 0. So given the matrix A, B, C, D, if this equation the quadratic equation has a solution lambda, then lambda is an eigenvalue. So you can find the eigenvalues by solving a quadratic equation. So for example, suppose the matrix ABCD is 5, 2, 2, 1. So A is 5, B and C are 2, D is 1. So we have lambda squared minus A plus B, 6 lambda, plus AD minus BC, plus 1 equals 0. Is that right? That's okay, but I want no, let's just see what happens. So what are the solutions? Lambda is minus b plus or minus the square root of b squared minus 4ac over 2a. That's just the quadratic formula. 6 plus or minus the square root of 32 over 2. Square root of 32 is 4 root 2. So lambda is 3 plus or minus 2 root 2. So these are the eigenvalues. If you take lambda to be one or the other of these, you'll get a solution. Let me take another example where we don't know quadratics. So I just pick one from the notes, which I'll post later today. Suppose we have the matrix 3, 2, 1, 4. So we define T from R2 to R2 by T of XY is 3, 2, 1, 4 applied to XY, which is 3x plus 2y, x plus 4y. And we want to find the lambda, if they exist, where this is lambda times xy. So we're solving the equations 3x plus 2y equals lambda x, x plus 4y equals lambda y. That's the same as lambda minus 3x minus 2y equals 0, minus x plus lambda minus 4y equals 0. This has a solution if the determinant, lambda minus 3, lambda minus 4, minus 2 times minus 1, that's lambda squared minus 7 lambda plus 12 minus 2, that's lambda squared minus 7 lambda plus 10 equals 0. But this is really lambda minus 2, lambda minus 5 equals 0. So we get eigenvalues, lambda equal 2, and lambda equal 5. So if these are the eigenvalues, they have to be eigenvectors. We have to be able to find x and y, so we have to solve the equations. Let's see, let's take lambda equal 5. When lambda is 5, we have to solve the equations 5 minus 3, 2x minus 2y equals 0, minus x plus y equals 0. Solution of this is x equal y. So if we take the vector x, y, x equal y, let's say 1, 1. What is t of the vector 1, 1? That's 3, 2, 1, 4, 1, 1. That's 5, 5. That's 5 times the vector 1, 1. So this is my vector, and this is my eigenvalue. T of this vector is 5 times the vector. So we have eigenvalue 5, eigenvector 1, 1. So what we're going to spend at least the next lecture on is trying to understand more about eigenvalues and eigenvectors. But for the 2x2 case, whenever you have any linear transformation from R2 to R2, solving a quadratic equation will always tell you what are the eigenvectors and eigenvalues if they exist, and it will tell you if they don't exist. Because it just depends on what are the roots of the quadratic equation. Okay. That is what we learned today. I'll post some more lectures probably over the week. Bye all.